curve on a surface theorem. So what's the claim? Well, let phi be a function from some subset U of the k-dimensional real space into the n-dimensional real space. And let it be a k-chart. And let some curve C, which is a map from some real from a subset of the real number line, some real interval, into phi of U. Right? In other words, or equivalently, C is a map from some real interval J into the image of phi, because of course this is the domain of phi as we have defined here. Now we also require that and assume that C is a parameterized, obviously, non-singular curve on some simple K surface. And it's not just any K surface, it is specifically phi of U. Some explanation of these terms might be in order. So, what does it mean that the curve is non-singular? It's very simple. It means simply that the first derivative exists everywhere and is non-zero everywhere. And secondly, it's a curve on some K surface phi U. Well, that's exactly what the definition says. We take the curve maps some interval onto the surface of phi. So if we have some crazy surface like this, some combination of sines and cosines, then the curve will live somewhere on the surface. There doesn't exist a single point where it would diverge vertically from the surface. Alright, let's keep on going. So these are our requirements, our assumptions. Then we have that U is equal to phi inverse after C. And it's a map which maps the interval I on which the curve C is defined, and it maps it into into U, the domain of phi, as might be easily deduced from this definition here. Now, this also is a non-singular parameterized curve in U, and it holds that C is equal to phi after U. Alright, so let's prove this. And perhaps an illustration would be in order. So, what are we actually doing? Well, imagine now that we have some plane down here. Well, it's not really a plane, it is a subset of a k-dimensional real space down here. Right, so let us assume that this plane is U, which is a subset of the k-dimensional real space. And somewhere above here, this cloud-looking thing will be some sort of parameterized surface. Let's say something like this. Now, we have our function, let's put it in blue, phi, which maps this surface, well, this plane, or this k-dimensional real space, or subset of it, up here. So phi is such a map. Okay. Oh, I would also remark that this is an n-dimensional real space. Or rather, it is phi of u, which is a subset of the n-dimensional real space. So this is function phi. Somewhere here on the side, let's put it in red, we have a real interval, I, and some map, C, it's a curve, which maps this interval onto this surface here. So something like this. And this is, of course, C. So, like this. Finally, we will have a last map. Let's put it in, say, purple. Another map which maps this curve up here down here. Onto a new curve which lives here. And this will be our curve U, or parameterized curve U. And what we wish to show is that U is a non-singular, and this is a well-defined parameterized curve, and that this equality holds. In other words, if I can take this interval, map it directly down here, and then move it up using phi, that this will be the original curve C. So that's a very interesting claim with some nice geometric interpretation. But how do we prove this, though? Well, the first claim we can get quite easily. So, 1, clearly what? Clearly U is a continuous map. As it is a composition of two continuous maps. Well, by definition, we have up here that U is defined as the composition of phi inverse and C. C is continuous by definition because it is a parameterized curve. All parameterized curves must be continuous. And phi is a chart, which means it's a homeomorphism. Specifically, then it has a continuous inverse. So so U is a composition of two continuous maps. Ergo, it is continuous. So this was quite easy. Now 2. Pardon me. Maps. 2. We wish to show that that U is of class C1. In other words, that it is smooth. Why? Well, smoothness of the curve removes any possibility of cusps or any such phenomena. So that's a very good thing. We require that. Because, yeah, we require that. It's necessary. It removes simply the possibility of odd things happening, like, as I said, cusps or intersections, or something even crazier, something like this, etc. It's a good safeguard. So we shall prove it. Now, how do we do it? It's quite straightforward, actually. Choose some starting point. Choose some starting point t0, which is an element of the real interval I, and denote x0 as the point of the curve C at t0, and we also denote u0 as phi inverse of x0. Now, we know, or by assumption, the rank of the Jacobian of phi at u0 is k, in other words, is the greatest possible. We know this by assumption because we assume that phi is a k-chart. And one of the assumptions of something being a k-chart is that the Jacobian is non-zero everywhere. That the Jacobian is non-singular. And has the greatest possible rank, which is this case. Now, we say without any loss of generality, log, the derivatives of phi I, these are the individual components of phi because it's a vector function, del phi I over del uj for all ij equal to 1 to k is non-singular. The matrix which we obtain like this is non-singular. Why is without any loss of generality? Because if it wasn't like this, there are k of them. There are k independent columns, so we would just rearrange them, right? It would just be a matter of a change of notation, which we can't be bothered with. We have more important things to do. So without any loss of generality, assume we already have everything in place. But if it weren't, we would know how to fix it. We'll assume that this is non-singular. Finally, denote, this is the last piece of notation, I promise, denote that pi is a function, well, a projection, that's why it's called a pi, of x1 to xn to x1 to xk. Essentially what pi does is that it takes an n-dimensional vector and it kills off the last few entries. So it has only k entries, not n entries, because k is smaller than n. It's some sort of projection, hence the name. Alright, pardon me, one last definition. We have forgotten to define G, and we define it as the composition of pi and phi. And now observe that both pi and phi are smooth, right? Phi by assumption and pi, because a map like this simply is smooth, because it very easily you could verify this. You could take the first and second derivatives and you would find that everything is nice and continuous and beautiful, right? This is actually C infinity continuous, but that's not important. Important thing is that G is a smooth function, or is smooth. Alright. Well, since it is smooth, we have that, we have that the Jacobian of G at u0 is non-singular. And thus, by local diffeomorphism theorem, we have that there exists G inverse on some neighborhood V of V0, which you define as pi of x0. Why does it exist? Well, because the local diffeomorphism theorem tells us that even there is a diffeomorphism happening there on a small neighborhood. Well, if it's diffeomorphic, then the inverse exists in particular. That's a very simple corollary of the definition of diffeomorphism. Now, also observe that we have essentially defined pi simply so the dimensions would fit. It's a purely technical definition. It doesn't have any real bearing on anything. It just there so the definitions fit. Now, or the dimensions fit. Now, we are nearing the end. G inverse composed with pi is phi inverse, quite clearly. It's because the definition of pi, of G is up here. And thus, okay, I can write this out explicitly. G inverse is phi inverse composed with pi inverse composed with pi, and this in particular then is phi inverse. And it works then on phi of u intersected with pi inverse of v. And now, well, it's a capital U, obviously, and a capital V, and this implies that U is defined as phi inverse composed with the curve C, and this, by definition, then, is G inverse composed with pi composed with C on some neighborhood of T0. Well, but this, of course, means that U is smooth. Now, quite obviously from here, we also get the desired formula that C is equal to phi composed with U. So we have a smooth curve with the defined by the formula we wanted. It is continuous, and from the non-singularity of everything we've used so far, it is non-singular itself, which is precisely what we wanted.